Assalamu alaikum. Let's start lecture number 13 for CS218 Data Structures and Algorithms. Today we are going to talk about stacks. We are going to use chapter 7 of book 1 for this topic. What is a stack? A stack is used to store data such that the last item inserted is the first item removed. The stack is a linear data structure which implements the last in, first out protocol. If you want to know about linear data structures, I advise that you go back to lecture 1. I have defined linear data structures in it. New items are added and existing items are removed from the same end, called the top of the stack. Let me show you how a stack works. This is a stack. First we pushed 12, then we pushed 74 on top of 12, then we pushed 23 on top of 74, and now we are pushing 19 on top of 23. In picture B, we are pushing 5 on top of 19. And this is the final stack after 5 has been pushed in. So whoever sees the stack will only be able to access the element at the top of the stack. If somebody wants to pop from this stack or to remove data items from this stack, when he does so, he will get 5. And if you pop again, you will get 19. If you pop again, you will get 23, always the top element. If you pop again, you will get 74. In the next pop, you will get 12. And then you cannot pop any further because the stack is empty. Things we never do with stacks. We never push data onto a full stack. This leads to overflow. We never pop data from an empty stack. This leads to underflow. We never traverse, search, or sort in a stack. We never use the other end of the stack for insertion or deletion. Only the top is used at all times. Implementing a stack. The stack ADT can be implemented using a Python list or a linked list. We implement the class stack with both underlying data structures with the same class function definitions in different files. The user may change the implementation of stack by importing the relevant file into his code. No other changes will be required. So first I am going to talk about a file called stackwithlist.py. I have implemented a class called myStack. And here I am implementing the stack with a Python list. So in the init function, I take a list called elements and I simply initialize it. Pictorially, this is what happens. The init function creates an elements named list in the object of the class myStack. And People might ask, how many bytes would this list take? How much storage would this list take? In Python, an empty list takes 72 bytes, even when it has not been given the number of elements that it will hold. So the interpreter will create a list and that structure will take 72 bytes in the memory. Top of the stack is not pointing to anything because there is no element to point to. And the creation of this object or the init function, this process is O1 because every time that you create the elements list, you reserve 72 bytes in memory. That takes a constant time. So the init function takes a constant time. Then I have a function here called isEmpty. The isEmpty function is supposed to tell me if my stack is empty or not. Inside, I just write one line. I call the len function for self.elements, and if the length is 0, the comparison will return true. If the length is not 0, the comparison will return false. Whatever the comparison returns, that will be the return value of this function. This function is O1. Why? Because it uses the len function, and the len function is O1. People might ask, how is the len function for a list O1? Because people might say that if a list has n elements, then we will have to go through the list to count the number of elements, and that would be On. But this is not how a compiler or an interpreter works. When a compiler or an interpreter creates a data structure, it stores the number of elements inside the data structure in a variable. And every time that you ask for the length of the data structure, it just returns the value of that variable. Returning the value of a variable takes constant time. So I can say that the len function takes constant time because the len function does not encompass a traversal through the data structure. It simply means going to the variable that holds the number of elements and reading its value and returning it. Then I have a push function. It takes the object of the class and a value. The push function is supposed to push this value onto the top of the stack. So currently this is the state of your object. Top of stack is element in index 2. And when you execute the push function, the new value comes to sit on top of the old top. So top of a stack now points to index 3. This function is O1 because you are only appending a value to an already present list. Then we have the pop function. The first thing we do is we check if the stack is empty. And if the stack is empty, we are simply not going to go any further. We will tell the user that the stack is empty and quit, because we will never pop from an empty stack. So assume that the stack has elements. Again, I am reiterating something I've said previously. Most of the time, when you remove data or delete data, this is actually retrieval of data from a data structure. And why do you do retrieval of data? You do retrieval of data because you want to use it. So when we are deleting elements from a data structure, we first store the value in a variable, then delete the holding item in the data structure, and then we return the value that we have just stored. So for this storage, I am using the variable x. Now look at it pictorially. Top of the stack is pointing to index 3, and then I bring in a variable x. I place the value from index 3 in x, and then top of the stack now points to index 2. So the value ceases to exist in the stack, but it comes to exist in the variable x, which I return. This function is also O1 because you are simply deleting an element from a Python list. Now I implement the same data structure using a linked list. So I create another file called stackwithlinkedlist.py. The name of the class is the same. The first thing that I do is I import the list node class that I created when I was working with singly linked lists. Look at the init function of this class. It simply initializes a top pointer to none. So pictorially, the object is something like this. Inside the object, I have a pointer that points to none because the list does not contain any elements. And since the linked list is implementing my stack, I can say that my stack does not contain any elements. This creation is O1 because it only encompasses setting a pointer to none. Then I implement the isEmpty function. This is easily done. I compare self.top with none, and whatever is the value of the comparison, I return it. If top is none, the comparison will be true and I will return true. If top is not none, it is pointing to a linked list. The comparison will be false and I will return false. Since this is just one comparison, isEmpty is O1. Now I implement the push function, which takes object of the class and a value that it is supposed to add to the data structure that is already present. The first thing that I do is call the init function of the class list node. The init function will create a node. This is pointed to by x. In the data field, you have val, and the next pointer is none. Now I make x.next point where self.top is pointing. Self.top is currently pointing to the first node in the singly linked list. Then I set self.top to point where x is pointing. Now if you start traversing from top, you will see that we have added the node containing val to the singly linked list in the mystack object. This is the final arrangement. You can see that we have added a new first node to the singly linked list that existed before. So this is an O1 operation. Hence we can say that the push function is O1. Finally, I code the pop function of the class. If the stack is empty, I tell the user that I cannot pop. Otherwise, I am going to store the element present in the first node of the singly linked list in another variable. That variable is x. After I have done this, I am going to make top point to the second node in the singly linked list. In other words, I am going to advance top. This has been done. Now if you start traversal from top, you will see that there is no pointer which will take you to the first node. So this means that the first node has been deleted. This is the actual picture. And then we return x. So what is the O notation of this function? We have deleted the first node in a singly linked list, which is an O1 operation. Hence pop is O1. Now we come to using one of the two implementations of my stack class. In the beginning, I have written two lines. From stack with list, import my stack. From stack with linked list, import my stack. You must have noticed that the functions that I coded in both the files were exactly the same and had the same list of arguments. So when I am using any of the two classes that I have implemented, I don't have to change the code that I am writing. I simply have to comment one of the two lines at the very beginning. Right now I have commented the first line. This means that the stack implementation that I am using is the linked list implementation. But if you comment out the second line and decomment the first line, then you will be using the stack implementation with Python list. In both cases, you will not have to make any changes to the code underneath the first two lines. So then I initialize an object of my class and I call it SL, and then I print SL.isEmpty. Right now the stack is empty, so true will be printed. Then I take a list. 5, 8, 4, 3, 7 are the contents of this list. And then in a for loop, I push these elements onto my stack object. Now I again print the empty status of the stack, which will be false because I have just pushed in 5 elements. Then I write a while loop. While the stack is not empty, it is supposed to pop data from the stack and then print it. And then it will again check if the stack is empty. Obviously it will be empty, so true will be printed. Now that we have implemented stacks, we are going to use stacks. So what are the common applications of stacks? Let us list some of them. Conversion of infix expressions to postfix expressions. Evaluation of postfix expressions. Execution of the quicksort algorithm. Transfer of control from one function to another and back. Implementation of recursion. We will explore these applications of stacks one by one. Now I am going to talk at length about mathematical expressions, their conversion and evaluation with the help of stacks. We have been writing mathematical expressions in one format all our lives. But the truth of the matter is mathematical expressions can be written in more than one formats. The format we are used to is called the infix notation. In the infix notation, the operator is mentioned between the operands. Something like this. A and B are operands and plus is the operator. We are discussing binary operators. Binary operators are operators which use two operands for evaluation. Addition is a binary operator. Can you think of a unary operator that takes only one operand? Let me give you an example. The square root operator is a unary operator. But we will restrict our discussion to binary operators only. So when we are working with the infix notation, we place the operator between the operands. And this is the notation that we are aware of. Another notation is called the prefix notation. Here, the operator is mentioned before the operands. So if you are writing a plus b in infix, in prefix, you will write it as plus ab. The operator, then the first operand, then the second operand. Then there is another format known as the postfix notation. Yes, you guessed right. Here, the operator is mentioned after the operands. So, if in infix we are writing a plus b, the postfix counterpart would be ab plus the first operand, then the second operand, then the operator. So the first thing that we have learned is that there are more than one ways of writing mathematical expressions. So how do we convert between formats? Convert the given infix expression to postfix. When we were in school, our teacher taught us a rule known as the Bottomless rule. Bracket open, divide, multiply, add and subtract. Remember that? This rule is used for infix expressions. So let us use the same rule here. This rule tells me that I should first concentrate on whatever is inside the bracket. Inside the bracket is C plus D. The postfix equivalent will be CD plus. So I replace the infix with the postfix. This is what I get. Now look at the green box. When I evaluate, CD plus is going to give me one number. Consider the green box to contain the result of CD plus. This is an operand. Now look at the second most important operator, that is the divide sign. The first operand of the divide sign is B. The second operand of the divide sign is everything inside the green box. I repeat, the first operand of the divide sign is B and the second operand of the divide sign is CD plus. B divided by CD plus. In postfix it will be written as BCD plus divide. This whole thing in the bigger green box. Now concentrate on the plus sign outside the green box. The first operand of the plus sign is A And the second operand of the plus sign is everything in the bigger green box. So when we write the postfix equivalent, this will be A, everything in the big green box, and then the plus sign. And this is the postfix equivalent of the infix expression that we were given. Convert the given infix expression to prefix. Again, I use the Bodmer's rule and I concentrate on the entities inside the bracket. C plus D. In prefix, I will write it as plus CD. Now consider everything in the orange box to be one number, and it will become one number after evaluation. The second most important operator is divide. The first operand is B, the second operand is plus CD. B divide plus CD. In prefix, it will be written as divide B plus CD, or everything that is inside the bigger orange box. Now we concentrate on the plus outside the orange box. Its first operand is A and its second operand is divide B plus CD. Writing it in prefix, we will write the operator first, then the first operand, then the second operand. And this will give us the prefix expression for the given infix expression. Let's do more conversions. Convert the given prefix expression to infix. I cannot use the Bodmer's rule because the Bodmer's rule is for infix expressions. What I do here is this. I start scanning from the left towards the right. I am looking for a pattern in which there is an operator followed by two operands. So first I look at the plus sign, but it is not followed by any operand. Then I look at the divide sign, but it is only followed by one operand. Then I look at the multiply sign, and this is followed by two operands B and C. This is the pattern that I was looking for. Multiply BC can be written in infix as B multiplied with C. Notice that I have used brackets because I can use brackets in infix. Again scan from the left going towards the right. There is an operator plus, but it is not followed by two operands. The divide sign is followed by an operand A and another operand B multiplied with C in brackets. This is the pattern that I am looking for, and the pattern in the bigger green box can be written in infix as A divided by B into C. Again I have used brackets. Again I start scanning from the left towards the right, looking for an operator followed by two operands. Plus is an operator. It is followed by an operand A divided by B into C and then another operand D. So this can be written as the first operand, then the operator, then the second operand. And this is the infix expression I was looking for. Convert the given postfix expression to infix. Again, I cannot use the Bodmer's rule because the Bodmer's rule is for infix expressions. Again, I start scanning from the left towards the right. Now I am looking for a pattern in which I have two consecutive operands followed by an operator. A is an operand followed by another operand, but the second operand is not followed by an operator. B is an operand followed by another operand C, which is followed by an operator multiply. This is the pattern I was looking for. BC multiply can be written as B multiplied with C. I have used brackets again. Start scanning from the left towards the right, looking for an operand followed by another operand and then an operator. A is an operand. B multiplied with C in brackets is another operand. Divide is an operator. So this is the pattern that I desire. This can be written as A divided by B into C. Again, I enclose the converted infix into a bracket so that I consider it one full operand. Again, scan from the left to the right, looking for two operands followed by an operator. One operand is A divided by B multiplied with C. The other operand is D and the operator is plus. This can be written as A divided by B multiplied with C plus D, which is the infix expression for my postfix expression. So far we have converted mathematical expressions, but what if we are asked to evaluate? Evaluate the given postfix expression. How do I do this? Scan from the left to the right, looking for a pattern in which you have two operands followed by an operator. Here you are. 1 5 plus will evaluate to 6 because this is actually 1 plus 5. Substitute the expression with the value. I have written 6 in the place of the whole thing inside the green box. Now 6 is followed by 8 and 4. 8 is followed by 4 and 1. 4 is followed by 1 and minus. So this can be evaluated. 4 1 minus is actually 4 minus 1. The value will be 3. Substitute the value here. Again scan from the left to the right. 6 is followed by 8 and 3. 8 is followed by 3 and minus. So this is the pattern that we were looking for. 8 3 minus is 8 minus 3, which is 5. Substitute the value here. 6 5 multiply is 6 into 5, which is 30. How do I know that the evaluated value is correct? Let's check. Convert the given postfix expression to infix. This was the postfix expression. We take 1 5 plus and write 1 plus 5 in bracket. Now we find the desired pattern in 4 1 minus. We can write them as 4 minus 1 in brackets. Now we find the desired pattern in 8 4 minus 1 minus, and this can be written as in infix as 8 minus 4 minus 1 whole. Now 1 plus 5 is one operand. 8 minus 4 minus 1 whole is another operand. Multiply is an operator. So this can be written in infix as the first operand, then the operator, then the second operand. And you can evaluate this is infix expression. It gives you the same value 30. Your task is to convert the following infix expression to postfix and prefix. This is the first task. The second is to evaluate the given postfix expression. Save your snapshot as your roll number lecture 13 and submit your response in the assignment titled Lecture 13 Tasks in Google Classroom. So what did we learn today? We were introduced to stacks. We implemented stacks using Python list and singly linked list. We listed several problems that use stacks for solution. We learned about different formats for mathematical expressions. We learned how to convert between formats, and we learned how to evaluate postfix expressions. You have to read the book, submit your answers to the tasks in this lecture, note your questions and put them up in the relevant online session, and email your suggestions to me if you have any. Take care. Allah Hafiz.